So we want to write a negation for the statement 6 minus 3 equals 3. So that's as simple as 6 minus 3 is not equal to 3. Number 2, write a negation for the statement all roses are red. So you got to remember that when you negate all, that you would use the word some. Because when you negate all, it's not none. It would be, the negation of all is some roses. So, pen not working. Some roses are not red. Number 3, we're supposed to write a negation for the statement some members of the class went on the field trip. So when you negate some, that would mean none, right? So no members of the class went on the field trip. If you're struggling with this, you might want to check out the chapter, and this was in section 3.1, I believe, about negation. And it goes through negating universal quantifiers, which this, universal and existential quantifiers, where it tells you how to negate some, and it tells you how to negate all. So that's what you could go back and review if you're struggling with this. Alright, so we want to negate the statement, if I fall in love, it will be forever. Now remember, you have an if-then statement in this case. Do you remember what to do with an if-then statement? So this is what we have, if P, then Q. Now the rules say that a negation of an if-then statement is actually a conjunction, so it would be P and not Q. So we need to identify P and Q. Of course, fall in love is your P, and will be forever is your Q. So if we write this statement in this form, in other words, we're negating an if-then statement. A negation of an if-then statement is not another if-then statement. So you would say, I fall in love, and now we're negating Q, it will not be forever. Now for problem 5, let's think about what we have going on here. So she applied and did not get a student loan. Notice the and. So we have a conjunction in our problem. You can think about this in terms of P and Q. Well, if you want to negate a conjunction, remember, you have to use De Morgan's law, okay? So that's going to be not P or not Q. Now again, what did I use? I used De Morgan's law. So anytime you negate a conjunction or a disjunction, in other words, an and or an or, and you're negating the entire statement, you have to do what, you can think about as distributing the not inside, but that changes your operator. Okay, so now I have to write this, not P or not Q. So she did not apply. Let me try that again. So she did not apply, or she got a student loan. Notice I had to negate did not get a student loan, which was she got a student loan. So next for problem 6 through 8, we're given a statement P, you will help me, and Q, I will help you. So we're supposed to write each statement in symbols. If you won't help me, then I will help you. And notice if you won't help me, right here, is a negation of you will help me, which is P. And then I will help you, which is Q. So if you won't help me is not P, okay? And notice this is an if-then statement. So I have not P and then my arrow for my if-then statement. Then I will help you, which matches the truth value of Q. Therefore, that's our result. Okay, next problem. So we let P again represent you will help me, and then Q, I will help you, and let's see what we have. It says, I will help you if you will help me. Now, if you think about that, that's an if-then statement. If you will help me, okay, you could write it, rewrite it. If you will help me, then I will help you. So first we got to get it in the right order for an if-then statement. Okay, so if you will help me, okay, that's your P. Then I will help you. That's the Q. So this is if P, then Q. Okay, notice here, you will help me again is P. Just as a reminder, I will help you is Q. I won't help you if and only if. So remember, we have an if and only if. That's what we have going on here symbol-wise. Now, I won't help you is a negation of I will help you. So that's going to be not Q, and then if and only if you won't help me, which is a negation of you will help me. So not P. So not Q implies, well, if and only if, not P. You can't use word implies, because if you do, you have to read it both ways. So not Q, if and only if, not P. So that's that biconditional. Okay, for number 9, we're supposed to use the P and Q from the problems we just did, 6 through 8. And I wrote it here to remind you what P was. You will help me, and then Q is I will help you. But we're supposed to write not P and Q in words. So if P is you will help me, then not P is you will not help me. And if you'll recall, this symbol is and then Q, I will help you. Notice we're not negating the Q, so, and I will help you. So if the negation is only with one of the component statements, then you only negate that one. You don't also negate the Q value. So you will not help me, and I will help you. All right, so we have not P or not Q. There's probably a couple of ways of handling this. You could use De Morgan's law and distribute that, and that might make it a little easier, I think, or you could write that in symbols directly. But if you wanted to use De Morgan's law, remember you take the negative inside and change the operator here. So we're going to have not P and not Q, which would be Q. And again, what did I do there? I used De Morgan's law. Now, I don't think that's necessary. I think you could write the statement as is, like this, say, it is not the case that, and then say, you will help me or I will not help you. Did you catch that? So you could say, it is not. So this, if you don't use De Morgan's law, let me write this in red. If you don't use De Morgan's law, you could say, it is not the case that, and then you write P, because it doesn't say not P, it just says P, you will help me. And then it's an or I will not, because of the not Q, help you. So that's if you don't use De Morgan's law at all. Now what if we do use De Morgan's law? Go back into what we were saying. If I distribute that negative inside or the negation inside, and it's really not a distributive property, but it just feels like that, taking that negative in, it changes your or to an and. So you would say, you will not help me, because it's negating P. So you will not help me. Notice this is an and statement right here after we used De Morgan's law, and I will help you. Now these two guys have equivalent meaning, and they're both correct. One I used De Morgan's law, the other one I did not. Okay, here are the problems that I prefer. Now, we assume that P is true and that Q and R are false. So when when it asks you the truth value of a particular statement in symbols, I think the best thing to do is substitute your true or false if you know that about each of your component statements. It tells me that Q and R are false. So I'm going to replace the Q symbol with false and the R symbol with false. So that gives me not Q, remember Q is false, and not, and remember R is also false. Now again, right here, Q and R are false. That's where I got that from. Now we know how negations work. A not false is a true statement. I'm keeping my and symbol. A not false is a true statement. And we know from our truth table for true and true, remember if they're both true, then that is the only time an and statement is true. So overall, this is a true statement. So for our next problem, number 12, R or P and not Q. So once again, I know P is true. I'm trying to circle it over here, and then Q and R are false. So I'm going to replace any P in my statement with true, and any Q in my statement and R in my statement with false. So here we go. R is false, so I have false, and then I have my or symbol just like in the problem, parentheses just like in the problem. P is true and not Q, and remember Q is false. And then you just have to remember the rules for whatever type of operation you have. So you have false, or, okay. The next thing I'm doing, y'all, is I'm going to go in here and change this not false to what? To true, of course, right? So I have true and true. Now, order of operations, just like when you're working with a math problem and simplifying, you need to do your parentheses first when you know the truth value of both of those. And you do, of course, it's true and true. And we know true and true overall is true. That's how ands work. Now, I still have my false statement over here, or true. Now, you have to remember how an or statement works. Ors, you only need one of the values to be true for the entire statement to be true. And so false or true is a true statement. So we know that number 12 is true. Now for number 13, we're doing the same thing. Okay, we've got P is true, and over here Q and R are false. So I'm going to, once again, I'm going to replace my component statements, P and Q, with their truth value. And this is essentially the same as completing a truth table, but since we already know the truth value, we're not doing the whole truth table, we're really just doing one line of the truth table. So P is true, and this is a biconditional, remember if and only if, and then P is also true, implies Q, which is a false statement. So let's handle this if-then statement. True implies false. In other words, we're doing our parentheses first because we know the truth values of both of those. And true implies false is, do you remember what that is? That's false. Now, if you need to go back to your truth table for an if-then statement, so if you have P and Q and if P, then Q, then if you have them both true, it's true. But if you have true and false, that's the only time it's false. If you start an if-then statement with a true statement, it is true. I mean, with a false statement, I said that wrong. It is true. But what we have right here is true if false. That's this line right here, and that is overall false. But now we have a biconditional. And on a biconditional, if you start with true, then false, that's false. If you start with false, then true, that's true. But then you're doing a conditional, that's overall. Do we need to look up the biconditional truth table? Let's write that down. So again, I have a P, I have a Q. This time I have a biconditional. Now, if you'll remember, the only time biconditionals are actually true is if both lines or both component statements are true. If one of them is false, then it's false. So, but if you have false, false, then it's true. Now what we have in this particular situation is this line, so overall that is a false statement. But you got to know those truth tables for biconditionals. That's how we get through this problem. All right, so order 11 through 14. Again, we're assuming that P is true and that Q and R are false. So I'm going to jump in my statement right here and substitute. So each time I have a P or a Q or an R or an S, whatever it says, then I'm going to substitute. Now, it might throw you off for just a minute because notice there's an S, but it doesn't tell us anything about S except in this problem. The truth value of the statement S is unknown. We don't know the truth value of S. Can we do it? It kind of depends on the problem. So hopefully they gave us something that we can complete, but let's plug in and find out. So we have that R is false. So I have an if-then statement that starts with a false, and then it says S, because we don't know the truth value of S, or R, and R is false. Now I'm going to tell you the truth. I already know, without even looking at this, if you have an if-then statement, remember, that starts with false, the answer is true. Now, it's not a biconditional. That's just a conditional statement. If you start with false, then your answer is true. A biconditional, that's not the case. But this is not a biconditional. Now, if you didn't see that right off the bat, you could still work with this situation. Or can you? Because if you have S or false, you really don't know if S or false is true or false. Because if S were true, true or false would be true. But if S were false, false or false would be false. So the thing is, this truth value really just depends on S. And so you have F implies S. But again, it doesn't matter, because if you start a truth and if-then statement, with false, the answer is overall true. So that's a fun problem. You really have to use your logic skills to get through that one. So explain in your own words why, if P is a statement, the biconditional P, if and only if not P, must be false. Notice you don't even know the truth value of P. So maybe we could consider every possible way of handling this. What if we have the situation that P is a true statement? Okay, so we're just going to assume that P is true. That'll be the first time we do it. And let's say the second time we do it, we assume P is false. Well, let's just break it down, right? Now, you might write this in a sentence, but this is the way I write my words. So here we go. So P, if and only if not P. So if P is true, that would be true if and only if. Now, not P has to be false if P is true. Am I right? That's the only way that can happen. Now, remember, for an if and only if statement, biconditional that goes in both directions, the only way it's true is if they match. So true implies false already breaks down. That's a false statement. Okay? So you could say in your own words, if you didn't want to write just the mathematical explanation, you could say, well, if P were true, then you would have true if and only if false, which is false. Now let's look at it the other way around. What if P were false? Does the same thing happen? So if P were false, we would start with false, and then we'd have if and only if. Well, if P is false, then not P is true, right? Well, we run into the same situation, just backwards. Again, if you have a biconditional, and if and only if, the truth values must match on both of them, and it must either be true, true, or false, false. Because the problem is, if you start with a true, and then if false is a false statement. And so we can't have a false and a true overall. That's false. So there we go. Again, you could write that in your own words. You could show me the symbols. Either one of those would be a perfectly reasonable explanation. Now here's an interesting problem to help you study for sure. So it says state the necessary conditions for each of the following. So we'll do these 4 and then we'll come back for another video to start problem 17. But here we go. A conditional statement to be false. Remember, I have to remind yourself what a conditional statement is. First of all, conditional statement is if P, then Q, right? So you have to know what conditional means. That's an if-then statement. Now, when is an if-then statement false? The only time that's false is if the antecedent, which in this case is P, is true, and the consequence is Q is false. That's what you have to have. You have to have an if true, then false. That's the only time we get a false result. Okay, now here we have a conjunction to be true. Ignore this vertical line, it's not supposed to be there. So what do we need for a conjunction to be true? Well, first of all, we need to know what a conjunction is, right? A conjunction is an and statement, so that's P and Q. Now, for this to be true, both of your components must be true. That's the only way an and statement is true, and that's something that you know, just put it in words, really helps you study, I think. What about a disjunction to be false? Well, remind me, what is a disjunction? A disjunction is P or Q, so disjunction are or statements. When are or statements false? Only when both statements are false. Remember, ors, if either one of them are true, doesn't even have to be both. If either one of them are true, then the answer is true. So the only time you get a false when both statements are false. Okay, and then the last one, what about a biconditional to be true? So biconditional, remember, is P if and only if Q. Now for a biconditional to be true, what do we need? We need the truth value of both components to match. Matter of fact, I mentioned that on the last problem that we just did, number 15. So if P were true and Q were true, we would get a true statement. If P were false and Q were false, we would also get a true statement. So both components must match for that to be the case. So if you'd like to see 17 through I don't know how much, come on back to part 2.